Hello friends, in this video we are going to study about the potentiometers. Potentiometers are a type of electrical resistive transducers. So in this video we will study its construction, its principle of working and the types of potentiometers and some of its applications. So let us start with our topic. Resistive potentiometers, also known as POT, they are a type of an electrical resistive transducers. So this word electrical resistive transducers are those devices which convert a non-electrical quantity into an electrical quantity. So potentiometer is a type of transducer which is converting the non-electrical quantity displacement or we can say resistance into voltage. Okay, with the help of potentiometers we can measure the displacement, any type of displacement like linear or rotational displacement can be measured. Okay, and it is a transducer which is converting the non-electrical quantity resistance into a voltage. Okay, now, the electrical resistive transducers, they work on the principle that they are measuring the changes in the value of the resistance, and with the help of the change in the resistance, they are measuring some other physical quantity. Now, if we define the resistance of a conductor, resistance R is given by rho L by A, where rho is the resistivity, L is the length of the conductor, and A is the area of the conductor. So, by any means, if we are changing the resistivity, length and area of a conductor, we are changing the resistance of that conductor. And by using the changes in the resistance, we are measuring any physical quantity. Okay. So those type of transducers which are working on this principle, they are called the electrical resistive transducers because they are measuring the changes in the value of the resistance, and with the help of that they are measuring the electrical quantity and they are doing the conversion. Okay, so resistive potentiometers or POT, they are a type of electrical resistive transducers. The resistive potentiometers, they consist of a resistive element which is provided with a sliding contact, and this sliding contact is called wiper. Now the motion of this sliding contact over the resistive element, it can be any of the types. It can be a translational motion or it can be a rotational motion. So on the basis of the type of motion of the sliding contact, there are two types of potentiometers: translational potentiometers, also known as linear potentiometers, and the rotational potentiometers, also known as the rotary potentiometers. So potentiometers which are involving the translational motion of the sliding contact, they are called the linear or translational pots. Pot is the short form of the potentiometer, and rotational, they are called the rotatory pots. Let's see the diagram for the linear and the rotational potentiometers. So this is the diagram for the linear or the translational pot, and this is for the rotary pot. Now in this linear or translational pot, you can see that we are having a wiper, and this wiper is moving over the resistance wire. Resistance wire is wounded around a mandrel, okay, and to this resistance wire an input voltage is being applied, and the output voltage, it is measured between the wire and the wiper, okay. So here the changes, the here through this linear or translation pot, we are measuring the linear displacement, okay, or the translational displacement, which is in the left and right direction, okay. In this way, it is the translational motion which is measured through the linear pot. Now through the rotary pot, the resistance wire, it is in circular in shape. Here it was in straight shape, okay, straight line, and here it is circular in shape. Now it is again wounded around the mandrel. Here we are having the wiper. This wiper is moving over this circular shaped resistance wire, and here we are measuring the angular displacement, okay. So through linear potentiometer, we are measuring the linear displacement, and through the rotary potentiometer, we are measuring the angular displacement. Now there are some potentiometers which are having the combination of the two motions, that is the translational and both the translational and the rotational motion, and such type of pots are known as the helipods. So in the translation, we see that the resistance wire, it is in straight line, it is a straight device. In rotation, we are having the resistance wire in circular shape. So in this helipods, we are having the resistive element which is in the form of a helix. So due to the helix form of the resistive element, it is supporting both types of motions, translational and rotational motions. So we can say there are three types of potentiometer: linear potentiometers, rotary potentiometers, and the helipods. Okay, whereas in the rotary potentiometers, the resistive element, it is circular in shape, so we can measure an angular displacement as small as 10 degrees. So as small as 10 degrees of angular displacement can be measured with it. Whereas in the case of helipods, because both translational and rotational motion can be measured, so these are the multi-turn potentiometers. And with these multi-turn potentiometers, a maximum value of about 3500 degrees of angular displacement, it can be measured. Now you have seen in the diagram of the potentiometers that the resistive element, we have connected an input voltage to it, which is the EI. Both in the linear and the rotary potentiometers, to the resistive element and input voltage is being connected, which is EI. Now this voltage, it can be an AC or the DC voltage. So resistive element, it can be excited by either AC or DC voltage. Now, if we talk about the general potentiometers, then a potentiometer, as I have said, that it is a type of electrical resistive transducer which is converting a non-electrical quantity into an electrical quantity. Also, this potentiometers or pot, they are a type of passive transducers. Passive transducers are those transducers which require an external source, external power source to drive the transducer. Okay, so these are a type of passive transducers, and they require an external source. Now the resistive body of the potentiometer, it may be a wire wound. Means you can see in the diagram that we were having the mandrel, and on this mandrel the resistive element is being wounded up. Okay, so the resistive body of the potentiometer, it may be wire wound, a very thin 0.01 mm diameter of. So the resistive body of potential, it may be wire wound, a very thin diameter of 0.01 mm of platinum and nickel alloy. It is wounded on an insulated former. There are also other alloys also which can be used for the making of this resistive body of the potentiometer. So this was just about the construction of the potentiometer, that what are the various parts in it. We are having a wiper, which is, or we a sliding contact which is moving over the resistive element, and to this resistive element an input voltage is being applied, and through the motion of the sliding contact we are finding out the value of the output voltage. Now let us see the working of the potentiometer. First we will consider here for the working the DC excited potentiometers. Linear potentiometer first we are going to consider, then we will see the rotary potentiometer. So here we are here in the diagram, a linear or translational pot which is excited by a DC voltage is shown here. Okay. Now here suppose E naught and EI, these are the output and input voltages. xt is the total length of potentiometer. Means total length of this resistive element is xt. Then xi. So here we have defined the different variables of the potentiometer, E naught, EI, output and input voltages. Here we are considering the DC voltages, so this voltage is in volts. Then total length of the potentiometer is xt, it is in meters. Displacement of wiper from its zero position, it is also in meters, and rp, which is the total resistance of potentiometer, it is in ohms. Now if the distribution of the resistance across the total length of the potentiometer, if here we consider that the resistance is distributed linearly over the entire length of the potentiometer, so if we want to find out the resistance per unit length, total resistance is rp and total length is xt. So the resistance per unit length will be rp divided by xt, because here we have assumed that the distribution of the resistance is linear across the total length of the potentiometer. Now the output voltage under these conditions will be E naught equals to resistance at the output terminals divided by the resistance at the input terminals and then multiplied with the input voltage. Okay. So here if we put the value of all the variables, E naught equals to resistance at the output terminal. Resistance at the output terminal will be Rp and the ratio of Xi by Xt, and the resistance at the input terminal is the Rp only, that is the total resistance of the potentiometer. Because when we see that in a potentiometer, when we are seeing from the input side, then we will see the total length of the potentiometer. So total resistance will be Rp. Now when we see from the output terminals, we are having the sliding contact. Okay, so only that much point where the sliding contact is being positioned, that will be the xi, that is the displacement xi upon xt, and then multiplied with the total resistance, that is rp, that will be the resistance at the output terminal. So here if we put the value, resistance at output terminal is Rp multiplied with Xi by Xt divided by Rp and then multiplied with the input voltage. So E naught will be equal to Rp and Rp cancelled, that is Xi by Xt multiplied with Ei. So you can see that under the ideal conditions, the output voltage, it varies linearly with the displacement. Okay. So here if we, because from this equation E naught by Ei is equal to Xi by Xt. So there is a linear relationship between these two ratios. So if we draw the graph between them, it will be a straight line. Okay, so you can see that the output voltage, it is varying linearly with the displacement. Now if we talk about the sensitivity of the potentiometer. So sensitivity is the ratio of output and the input. Output is what? E naught. Input is what? EI. So E naught by EI is Xi by XT. Okay, so this is the sensitivity of the potentiometer. Now here also from this equation you can see that the sensitivity is constant under the ideal conditions. Ideal conditions, here we have assumed that the distribution of the resistance is linear across the whole length of the potentiometer. So that is the assumption which we have taken earlier. Okay. So this was the case when we are considering a linear potentiometer. Now if we consider an angular or the rotary potentiometer, instead of linear displacement, there we will have the angular displacement. So xi, instead of xi, we will be having theta I. Instead of xt, we will have theta t. Okay. So in that case, for rotary potentiometers, the equation will be changed. The output voltage E naught will be theta I by theta T multiplied with the EI. Okay. So whether we are considering a linear or translational potentiometer or a rotary potentiometer, we have seen that the output voltage, it varies linearly with the displacement. So if we are measuring the displacement of the wiper, we can measure the output voltage. So here you can see that I have told here earlier that this potentiometer, it is an electrical resistive transducer. So resistance was, I have told, rho L by A. So if we are varying any of these physical quantities, we are varying the resistance. Okay. So here we have changed the length. We have changed the length of the conductor by moving the sliding contact. So by changing the length, we have changed the resistance, and through that we are measuring the displacement. And this displacement is converted into the output voltage. So because it is using the resistive principle, that is why it is called an electrical resistive transducer. So this equation E naught equals to theta I by theta t into EI, or in the case of linear, E naught equals to xi by xt multiplied with EI. This equation stands for the case of potentiometer which are having only a single turn. Okay. So in linear, you have seen that we are having only a single turn of the resistive wire, and in the rotary potentiometers also we are having single turn. Whereas in the case of helipods, we are having the multiple turns or multi-turn potentiometers. In those cases, this equation doesn't stand. So this is for the single turn potentiometers only. Now these potentiometers, the circuit which you have seen for the linear potentiometer, this circuit is known as the potentiometer dividers. So these linear potentiometer circuits, these are known as the potentiometer dividers because they are dividing the input voltage because they are producing an output voltage which is a fraction of the input voltage. The equation which we were getting was xi by xt into EI. So you can see that the output voltage, it is a fraction of the input voltage. Also you can say that the input voltage, it is divided by the potential by the potentiometer circuit. So that is why they are known as the potentiometer divider or the potential dividers. Okay, so these circuits are known as the potentiometer dividers or the potential dividers. So if we define this device, a potential divider is a device which divides the potential. So potential divider is a device which divides the potential into a fraction, and this fraction or ratio is determined by the position of the sliding contact. Okay. Now the equations which we have derived through this potentiometer, E naught equals to xi by xt multiplied with ei, and also E naught equals to theta I by theta t multiplied with ei. This rotary and the linear potentiometer equations, these equations are under the assumption that the resistance of the potentiometer, it is linearly distributed over its entire length, and also the resistance of the measuring device, the voltage measuring device, that is infinite. But practically this never happens. The device which is used for the measurement of the voltage measuring device, it has some value of the resistance. Okay, so let's see that what is the effect of this resistance on the measurements. Okay, so this is the linear potentiometer, in which we have considered here that the output device which is measuring this output voltage, it is having some value of the resistance which is called the Rm. Okay. Now in this case, the resistance which is seen from the output terminals, that will be changed. It will be given by the parallel combination of this Rm and the resistance of the potentiometer, that is Rp. Okay, so this is Xi by Xt. So when we are seeing the resistance from the output terminals, it will be a parallel combination of Rm and the Rp multiplied with this Xi by Xt. Okay. So earlier when we have done the calculation, E naught is equal to the resistance from the output terminal, which was Rp multiplied by Xi by Xt, divided by the resistance from the input terminal, that is Rp, and multiplied with the input voltage EI. Now here the resistance from the output terminal has changed. It is the parallel combination. Okay, and this ratio Xi by Xt, we have replaced it by a constant K. So K Rp Rm by K Rp plus Rm. Okay, so this is the parallel combination. Okay, now the complete resistance seen from the terminals will be R equals to Rp 1 minus K plus K Rp Rm. So this is the total resistance which is seen from the source. Okay, because here the parallel combination of this plus the Rp 1 minus K factor is also there. Now solving this, when we solve this, we will get the equation K Rp square 1 minus K plus Rp Rm upon K Rp plus Rm. Now the current. Current is equal to the voltage upon the resistance. So input voltage is EI and resistance is R. EI, putting the value of R from this equation, we will get EI K Rp plus Rm. This is the current. Now output voltage under these load conditions, that when we have you consider the resistance of the output measuring device, so E naught will be equals to I K Rp Rm upon so output voltage E naught is equals to I K Rp Rm upon K Rp plus Rm, that is a parallel combination. Okay, E equals to IR, here we have written. Put the value of E from this equation. Multiplied with this factor. So this will be cancelled. So here you can see that the output voltage E naught is equal to EI K Rp Rm upon K Rp square. So E naught upon EI. When we simplify this, we will get this ratio. So from this equation, you can see that there is a non-linear relationship between the output and the input voltage. Earlier, we have got the equation E naught by EI is equals to, we are having Xi by Xt. And Xi by Xt is the constant K. Okay. Now here we are getting a different, we are having this denominator factor also. Now here if we consider that this ratio Rp upon Rm, it is very much infinite. If we consider that this is infinite, then this will be reduced to the constant K only. Okay. So when we draw the characteristics, we will get the linear relationship when this Rp upon Rm, it is equal to infinite. Now as this ratio it decreases, this comes to a non-linear relationship. Okay, so as this ratio is decreasing, Rp by Rm, this linear relationship will become a non-linear relationship. So you can see that how a non-linear relationship is coming out between E naught and EI when we are considering the resistance of the output measuring device also. Okay. So this was the working and the output equation of the potentiometer, that how a potentiometer is measuring the displacement, how it is checking the converting the displacement into a output voltage. Now comes the construction of potentiometers. You have seen here that in the potentiometers, a resistive element, it is wounded across a mandrel. Okay, so here we are having The resistive element which is used to wound across the mandrel, this resistive element, it is a single wire of conducting material. So the main element or the main component of potentiometer is the resistive element, which is a single wire of the conducting material which gives a continuous stepless variation as the wiper travels over it. Now, in case of such potentiometers, in the case of translational potentiometer, which are the straight devices, so we have to use a straight material, okay, over that insulated former, the resistive element is wounded. Also, in the case of the rotational potentiometer, this resistive element has to be wounded spirally or in the circular shape around the insulated former. So this length and diameter of these potentiometers, it restrict their use on account of the space considerations, that they will acquire more space in that. So instead of doing this, we use wire wound potentiometers. In the wire wound potentiometer, the resistance wire, in the case of wire wound potentiometer, the resistance wire is wounded on a mandrel or a card in the case of translational potentiometers, and in the case of rotational, this resistance wire, it is formed in a circular shape. Okay, so what is the advantage of this wire wound potentiometers? That the variation of the resistance, it is not only continuous, not only linear continuous change is there, but also it is in the small steps. Okay, so that is why instead of having a very large size of a straight device or very much circular in shape, which is acquiring a very large diameter and large space is acquired, what we do, we use wire wound potentiometers in which the resistance wire is wounded across it, and these not only give the continuous variation in the resistance, but also this variation is in small steps. So this is how the potentiometers are constructed. Now let us see the materials which are used for the construction of potentiometers. The materials which are used for the construction of potentiometers, they are categorized into, one is the wire wound potentiometers, and second is the non-wire potentiometers. So in the wire wound potentiometers, they carry large currents at high temperature. The resistance temperature coefficient is also very small, and the resolution in the case of wire wound potentiometer, it is limited by the number of turns. Also, in this wire wound potentiometer, the material which is used for the construction of potentiometer, it is platinum, nickel chromium, or an alloy of these metals. Whereas in the non-wire potentiometer, the resolution and the life of the potentiometer is very good. Also, this resolution is not limited by the number of turns. They are known as the continuous potentiometers. And the materials which are used for the construction of the non-wire potentiometers, they are cermet, hot molded carbon, carbon film, and thin film carbon metal. So here you can see the difference between the wire wound potentiometers and the non-wire potentiometers. Now let us see the advantages and the disadvantages of the resistive potentiometers. So the advantages of resistive potentiometers are they are inexpensive, they are very simple to operate, and they are useful for the measurement of large amplitudes of displacements. They are having very high electrical efficiency. They also provide sufficient output to permit the control operations. In wire wound potentiometers, we have seen that the resolution is limited, while in the non-wire potentiometer, which are using the cermet and the metal wire configurations, the resolution is infinite. So these are the advantages of the resistive potentiometers. If we talk about disadvantage, the main disadvantage of the resistive potentiometer is that in linear potentiometer, a very large force is required to move the sliding contact. So the main disadvantage of these resistive transducers in the case of linear potentiometers is that the sliding contact or the wiper, a very large force is required to move these wipers, and also these sliding contacts, they can be contaminated, they can wear out, they become misaligned, and also they can generate noise. So these are the disadvantages linked with the resistive potentiometers. So in this video, we studied about the electrical resistive potentiometers, resistive transducer, that is the potentiometers. We studied its construction, its working, its applications, and the types of potentiometers, and then its advantages and disadvantages. So I hope that this topic is now clear to you. Thank you.